Okay, hi guys. So in this lecture, or rather this lecture was the last lecture which we'll be seeing in our Schrodinger wave equation. Then we'll be starting off with uh, second part of stoichiometry, which is nothing but redox reactions and several type of titrations which we'll be seeing. So let's get started with first closing off on Schrodinger wave equations. So starting off with some notes here that um, for closeness of an orbital with nucleus we use R average so that we can predict with the R average with the help of n plus L rule. And lesser the value of R average, more closeness of orbital or more penetration power of that orbital into the nucleus. Okay, so for closeness of orbital with nucleus we use R average. Okay, so from here we can predict. So the value of R average we can predict with the help of n and L rule, or rather n plus L rule as well. Okay, so lesser the value of R average, more closeness of orbital. Okay, or rather we can say more penetration power. Okay, so we can also write that less energy of orbital, more close with nucleus. Less energy of orbital, more close with nucleus. Okay, so R average in case of three S, 3P and 3D, the graph of whose we saw in the previous lecture would be in the order of 3S, then 3P, then 3D. Okay, so this would be the value of R average. Okay, and similarly value of R average, or rather the order of R average for 1S, 2S and 2P would be 1S, then 2S, then 2P. Okay, so in this case obviously we compared the R average in case of the same orbit, which was n equals to 3, and in this case when we are comparing the value of R average for different orbits like 1, 2 and 3, or different n values, obviously it would be of the order this. Okay, so please note that we calculated the value of R max in the previous lecture as 3S greater than 3B than 3D, but when we calculate the value of R max, R average, we'll be seeing how much closer the orbit is with the nucleus, and depending on that we'll be taking the value of R average. Okay, so the last topic for ending Schrodinger wave equation chapter would be R theta phi, which was angular wave function. So let's see something about it. So first it would be that we'll be drawing the boundary surface diagram, and secondly we would be drawing the electron cloud diagram. So for boundary surface diagram, it would be let's say for 1s it would be this, and for 2 it would be something like this. Okay, and for 2p it would be something like boundary surface diagram would be like this, and the electron cloud diagram would be like this. So I hope you know or remember the dumbbell shape of 2p orbital. Using the same, we are drawing the two diagrams. Okay, so with this we come to the end of this chapter, which was Schrodinger wave equation. Next we'll be starting off with second part of stoichiometry. Stoichiometry part 2, which mainly deals with redox reactions. Okay, so stoichiometry can actually be classified into two sub branches. First is gravimetric analysis, and second is volumetric analysis. Okay, so gravimetric analysis is based on measurement of mass or mole, and this is based on measurement of volume. Okay, so we also have a third category, which is titrimetric analysis, or rather we can call it as titration. Okay, which can be seen as a part of the second category as well. So this is titration. Okay, but some of the examples of this may include measurements of mass or mole as well. So we are not defining it as a third category, but as junction between the two, or something as it can be also be seen as a part of either of the two or both. Okay, so let's see some of experiment, or other experiment in which we have a burette. This is a stand, and we have a burette here. Okay, in which we are pouring some liquid onto a vessel. Okay, so this is the knob of the burette. Okay, and these are the measurement labels on the burette. Okay, so this is, let's say this is some standard solution. Okay, of titrant, which is a known solution. Let's say it as solution A, and this, so this is a definite volume of annihilate. So let's call it solution B. So A moles of solution A, so solution A is dropping off from here, which is getting mixed with solution B. So A moles of solution A on reacting with B moles of solution B produce C moles of solution, C moles of C plus D moles of D. So this is a balanced equation. Okay, and if you simply write A plus B gives C plus D, this is unbalanced equation. Okay, so at equilibrium point what will happen is that so at equilibrium point what can we say is number of equivalents of A, the titrant, would be equal to number of equivalent of B. Okay, so A is nothing but titrant and B is annihilate. Okay, so this is the equilibrium point, so in which neither A nor B remain in the beaker at equivalent point. Okay, so this is another way of seeing the same. So with this we come to the end of this lecture. In the next lecture we'll be seeing more on redox. So till then, good luck and goodbye.